Abacus tutorial workshop 1. In this workshop we are going to simulate a fire test of a simple beam exposing fire. When you complete this workshop example, you will be able to do the following tasks using Abacus CAE. So this workshop will somehow cover all the necessary things that's needed in both structural analysis and thermal analysis. And this is the case of a simple beam simply supported, and it is loaded in 4 point with 4 loads, and the 3 side of the I-beam is exposing fire. And so we follow this Abacus standard and then follow each module. In this simulations we follow the standard Abacus CAE procedure. So at first we model the part from the part model, then property, assembly, step, interactions, loads, and mesh definitions, and then we check that everything is okay, and then we run the job. So before creating the 2D cross section for this problem, so only 2D cross section of the beam is modeled for a 2D heat transfer problem, and before and for that one we go to the part module in Abacus. Okay, this is the Abacus and it's already open. So here are the modules, each modules, and we start from the part module, and then we start to create a new part. So in this one we create a part, and so the part is 2D, the modeling space is 2D planar because we are only considering the 2D cross section of the beam, and the type deformable, and the base feature is the cell, and the approximate size 200 for the grid. Then we continue, then so we are in a 2D sketch form, and here are the drawing tools for sketching the 2D cross sections, and this is the model tree, and it can be also, for example, we can create a part with a double click in the part, and then it's the same way, for example, if you do it from here. So let's create the beam section, so name the beam, and then the 2D same, continue, and then let's create yeah, you can even select the plane you like, and okay, so this is, so here are many things like trim, so let's trim this one. So now you can zoom in out. So let's say this is, let's say 0 0, and then we have the dimension of the cross section is the length is 125, so 125 0, and then the height of the flange is 9, so we can do it later. And then let's do just some arbitrary drawing, and then we can use the constraint to make this. So a little bit down, and I also want to, okay. Now we have the rough cross section of the beam. Now we can, here are some constraints, so we can add some constraint. So I like to make equal length, so click this one and then shift, so this is this to equal length, click this, and this is also equal length, and these four are also equal length. And so here, so let's undo it, and this okay, okay, yes, okay. The part is not done. Okay, so let's create it again. Beam, JP Maple, and then we say 0 0, and then this is 125 0, the height is 9, so 120 sorry, 125, then 9, yes. Okay, so let's do this one, and then this, some arbitrary drawing, because it will be easy when you draw using, okay. So let's do some constraint. So this equal length, this and this, yes, so equal, this and this equal length, this and this equal length, okay. And dimension, auto dimension, so this is 125, that's fine. This is done. This is done and done. So we have the sketch. So we can also edit the sketch from here, and let's make this dimension so this is 125, and then we add so this and this, so this and this, so this is so using these tools we modify the dimension, and then we partition these two faces so that it will be easy to mesh uniformly. Okay, we change the dimension and we confirm, and then there is a partition face, so by edge or face, and we can draw two straight line, here, here. Okay, okay, and the partition is done. Yes. Okay, the beam part, the beam part is model, the cross section. Now the next step is to define the thermal material properties and the section properties in the property model. So in the property model here we create a material, and then material name, it's steel, and then we add the density and thermal material properties, conductivity, specific heat, and for we don't use temperature dependent density, but for thermal stress density is needed, conductivity, and the specific heat, and temperature dependent, so we toggle this temperature dependent data here, and then use the data. So the density of the steel density is we use the density value in same unit systems, and the conductivity so paste this data from the table, and this specific heat we paste it from here. So the thermal material properties, conductivity, and specific heat necessary for thermal analysis for steel S355 is model. Okay, then we need to create a section which is homogeneous solid, and we define the material that we define in the early one for the material definitions. Okay, so here you can see the steel is defined, and then also the section homogeneous for the solid sections. We can also edit it and see the metal definition and type of section. Okay, so we are doing only thermal analysis, so we don't need to define this other part which is used in the structural analysis, but we have to assign this section what we have defined in the material. So we have to assign the sections. So we create a set. So the set is beam set. Okay, the beam set, and we say create set, so it will create a set, and then we select the face with mouse and the shift button. Okay, so this is selected, and then we click on the done. So we have named it as a region as a beam, and we have created a set, and the section is section 1 that we have defined, and this is solid homogeneous section with the material properties S355 what we have defined. Okay, so we don't want to do here, and so that's the first part model is defined, and the property model is defined. Okay, all right. So far we have defined the part and the part and the property definitions. In the property model we define the material properties, and in the material properties we have defined the thermal material properties for S355 and the three material behavior using conductivity, density, and specific heat. We have defined using these three keyword: conductivity, density, and specific heat. And the conductivity is defined as isotopic type, and we use the temperature dependent data, and we define the temperature dependent conductivity for this material, and these data are taken from the based on the equation given in the annual report 2019. So you can follow that one and get and also you can get this temperature data from the table. So we use three material behavior: conductivity, density, and specific heat to model the material behavior for thermal analysis. Okay, and now we have assigned a homogeneous section uh, to to the face, because we are going to assign all these faces as a homogeneous. And for that one we need to also define the material properties, and we have assigned the material S355 for the section, and finally we have assigned this section that we have defined to the beam. So the beam is the set of faces of this face, these all faces. Okay, so the next part after the property is the assembly model. So in the assembly model we have to create the instance. So you can create the instance from here below the module, or also you can create the from here also. So if you click in the model tree, there is, you can see assembly and instance, and if you double click the instance, then you will see this create instance box appear, and you have two options: create instance from part or the module. So we are going to create it from the module, and then instant type. So you usually have two type of instant type depending on mesh and part or mesh on instant. So this is very simple part, so it doesn't matter whether you define in independent mesh or independent mesh. So if we have many parts, then it's sometime we, if you like to mesh in the assembly, then you have to make independent or dependent, because like if you want to mesh every part and then assemble, then you have to make independent, and if you want to make dependent, and then you have to make it dependent. So okay, we say dependent on mesh part, then we apply. So our instance is created here, the beam instant one. So this is created, then okay, this is instance is created, and after the instance created created we go to the another model, that's step model, and alright, so we have defined the material, and now we have defined the assembly model, created the instance, and the step model here. So in this model, this is very important because we have to define what we are going to do, what type of analysis are we going to follow. So so in the step model, we define we assign the proper type of analysis, and the step is needed in order in another step to create different interaction and the loading for each step. So the abacus uh, uh, want us to assign the step after the assembly module. So let's go to the step module. Step module, yes. And then the step module, you can also define it from this model tree, but it's easy from here also. So it's depend on how you want to use. So this is the manager, step manager, and a fill output manager, and history output manager, and these are the some partition you want to do, and some other geometry datum and that kind of things. So we click here, then the step one. So this is our fire step, because we are going to apply the time temperature curve from the Cong fire experiment data, and this is general, and the solution procedure is a heat transfer. So you, for example, here we have linear permutation and the general. So the linear permutation is used when you solve the eigenvalue problem, and heat transfer is the good one for here. And we are not going to do these coupled temperature displacement or things, so we are purely doing heat transfer analysis only. So we select the heat transfer procedure and then continue. Then the step is there. So basically the description and incrementation and other parameter for equation solver, solution technique, and that kind of thing. So but at first we just because our analysis type is a transient analysis type, because the we are looking the temperature distribution over the time. So it's so, and the time is that we are going to simulate for 1 hour, which is 3600 second. And then we are going to use this automatic time integration. This is needed because if you cannot, if you don't define this type of heat transfer incrementation, then the solution will stop, it will not converge. So I like to put the initial step 1 increment size and the maximum size, for example 5, and the minimum size, okay, I leave it as this one, and then 10, okay, and 0.1. So that's all for the step. So we have defined one step, the initial step, and then the fire step. And the initial is the initial zero condition, and the fire step is a heat transfer transient analysis. So it really doesn't matter the non-linear geometry is on or not, because we are only doing the heat transfer analysis. And that's all. So then we need to have output, so this will automatically create. And then so you can see here also the NT is the temperature temperature distribution in the mesh. So by default it will select this NT, the thermal parameter. But if we using a keyword, then we have to select automatically for this temperature distribution type of data. Okay, that's all, and dismiss. So we can see the keyword from this model, because so in the report the keyword is mainly given. So for example, you can see that the keyword part is used to model the part, then assembly, then instance. So that's what we have done. And then we have defined the material properties, still as 3-5 and using a 3 keyword conductivity, density, and specific heat. And we have defined the temperature dependent data. And now next what we have created is a solution step in which we are doing a heat transfer procedure, and we have defined the in time of the solution time and some parameter definition in the US. And then we request the output request that we want to have the default output for the temperature analysis. Okay, that's all right. So we have created this step model, and now the next one is an interaction model. And in this model we are applying the boundary condition for the convection and the radiation heat transfer. So the convection and the radiation due to fire are applied as a boundary condition, temperature bound condition, and we with the amplitude curve that describe the gas temperatures. So in order to proceed that one, first we have to know how to create the temperature curve. for creating the gas temperature, and then define the boundary convection and radiation heat transfer coefficient, and along with the temperature curve. Okay, so okay. Okay, so the interaction model is here after the step model. The interaction model is here, and here you can see that here is an interaction manager, and here is an interaction property manager, and here's a constraint manager, and these are the things what you manage. But and these are the like different interaction properties what you can apply in your model. So before doing that one, in the model tree, we like to create an amplitude because we are going to create the temperature curve, and then so the fire temperature curve from Cong. So let's name it as a Cong fire, and I like to have a tabular form of data. And here we have a step time. So if we have a different step in our simulation, then we have to choose step time or the total time. So let's, in this case, let's say total time. And smoothing, we use the solver default. And let's say we have a frequency and the amplitude. So the frequency is the time and amplitude is the temperature. And for this one, we have the amplitude, the Cong fire, the temperature fire. So we can use the table data and then just copy and paste. So this is the temperature and this is the fire temperature in degrees Celsius, time and degrees Celsius. And okay, so we have the Cong fire, and now we can define the interaction. So so we have to define the convection and radiation for the fire exposed size and the fire that is not exposed. Okay, so the the interaction property model is here. So let's name it this as a convection to exposed side, exposed side. So and the convection boundary condition is model as a flame condition. So we select the type as a flame condition, and then we continue, and then the flame coefficient is there. So the flame coefficient is 25 for 25 the standard unit, SI unit 25, and we define this one, and then we okay, the flame condition is defined, and then edit, and we have to define this. So we have to define so this is the property defined, and now we have to define this flame convection exposed side, and the step is fire. We have, because that's the reason why we have to define the step, the fire, and surface flame condition and surface radiation condition for the convection boundary condition and the radiation boundary condition. So these two are needed in a fire analysis. So the surface flame conditions, and we have to apply to the surface. So let's say this is exposed surface. Let's create a set of line, exposed surface. So the exposed surface is, if you put the mouse over there, it will become red, and then you can select. And for the selecting, you will have to use the the shift button and then done. So now then after that, we have selected the surface that is exposed in the fire, and then we can do this property of reference or embedded coefficients. So if we do the property reference, then there is a film interaction property that we have defined earlier, and also we can do the embedded coefficient. So if the film coefficient is not dependent in the temperature, then we don't need to define this property, and we can directly do this one. So let's do the embedded, and for the 25, and this and the sink temperature is a Cong fire, and the sink uniform and sink temperature each one. So that's the definition for for the convection coefficient at the exposed side. So yes, and okay, so we apply that one, and the upper side is on exposed side. So let's create another on exposed side convection to an exposed side, and we always need to think that the step is correct step and surface film condition, and then the unexposed we say we create surface, and we select these surfaces, and then the 9, and then yes, the 9, and there is no temperature, fire temperature for this one. So it's 9, and it's uniform, and the sink temperature is 20, and we select the intenseness for the sink amplitude because there is no temperature curve for that one. So that's defined, and then another, again we have to define the radiation. So radiation, and that's defined using a surface radiation, and the radiation, so we have already defined the surfaces, so you can see it from here, the exposed and unexposed side. So exposed side, so if you click on the highlight selection view in the viewport, then it will highlight, then continue, and then we have to define the emissivity for the which is 0.7, and the ambient temperature is 1, and the Cong fire is the ambient temperature amplitude curve. Okay, so you can see here we have defined convection, and exposed and unexposed, and the radiation, so 3 interaction, that's because of the fire. Okay, and now we move to the load module. So in the load module we create initial temperature field in the initial step to assign the initial temperature field. So in our case, the initial temperature of the cross section is 20 degree, so we have to define for all the nodes as a 20 degree. So in order to do that one, so we go to the load module, and there are different modules. this is to define the predefined field, and so we select that one, and it's the initial model, and this is initial temperature, and we select the temperature, continue, and this is beam geometry because it's all, so all, and then so here initial temperature, that's the name, and the definition of this predefined field is a temperature field, and it's defined in the initial step of the solution procedure, and in the beam which means that whole beam, and it will assign a 20-degree temperature for all the nodes that's inside this part, and this is direct specification. Distribution means we define directly. There are other options also from previous result and also the function, but we don't need this one, and we say this is constant through the value, and the magnitude is 20 degrees Celsius. So that's done. We have defined the load model, and the next model is the mesh model. So in the mesh model, we create a mesh, assign the number of mesh and the seed type, and also we define the element properties. So in this one we define the heat transfer element. Okay, so now we go to the mesh model. So in the mesh model, so here you have a different option for the seeding the part. So seed the instant, and here you have the seed the edge, and you have here mesh instant. So this is the mesh part or instant, and then we have here the for the definition of the element types. So in mesh, so the it's in the part, or so let's, this is in the part, so we have to say the part model here, and then we select the global seed, so the and the sizing control for the mesh. So approximate global size, let's say for example 3, apply. So this should look fine. Okay, and then let's define the mesh for the whole geometry, and the element type, we are doing the heat transfer analysis standard using a standard solver, not with the explicit one, and the order of the shape function is a linear or quadratic. So in this case I think linear would work fine, and the linear, and we just leave it default. So we have selected a 4-node linear heat transfer quadrilateral element for the heat transfer analysis. Okay, and okay, so that's all, and we mesh the part. So 406 element have been generated in the part. So let's say we like to query about the mesh is okay. So here you can see that you have this definition. Okay, so let's say this beam continue heat transfer. Okay, dismiss, and we select this mesh heat transfer. Okay, so now let's query again, mesh done. Yeah, so the element, total number of node and the element, you can see it from here. 406 linear quadrilateral element type DC 240 is define everything, then job. So now it's time to write the input file. So before doing this one, I like to save this one as okay. So we have already there, but we can, so let's create a job. It's from name of the job is it will be the input file name. So the name of job, say like a test heat transfer test heat transfer, and the model, the source is the model. Or and we can also, for example, if we have to submit a job using an input file, we can do it in the input file, then continue. So this is the edit job button. So the name is test heat transfer, so this will write uh, this, and full analysis in the background immediately. So we don't need to print the echo, and the result file is ODB, right? ODB memory, it's okay. 90% of the physical memory and parallelizing. So how many CPU, if you want to use more CPU, then you can select it from here. And the precision, so it has full single precision or the double precision. So it's a single, it's okay in this one. So heat transfer analysis, then we monitor, and the monitor button. So yeah, this is the monitor button. And also in the manager, so you can click it from the manager, and then we can do the model check. Yes, the model attribute absolute 0 must be set. It is required for the following interaction radiation. Yes, so that's very important in any type of heat transfer analysis. Therefore we go in the model and then edit attribute, and here are the two things that's always needed in the heat transfer analysis, and they are the absolute 0 temperature, which is minus 273.16, and the step in Boltzmann constant 5.67 e to the power minus 8. So these are in SI units. Okay, so that's done. Then we go to this job and data check, and okay, yes, we like to do without history, and then it's checking, check submitted, and the check is running. And if we check completed, so this means that you can see also the status over here. So let's make this one a little bit big up. So here you can see the status, and check count completed. Okay, then we submit this job. Okay, yes, and it's submitted. Then we can monitor. So here you can monitor if you have some error and what's going on. So here we have write the input file, and then the Abacus standard solution procedure is started, and you can see the step and the increment and the time. So it says too many increment to complete the step. So this is error, so which means that we have to again check our step model and the heat transfer. So this is and what was and so we have to increase the maximum number of increment, so I like to make it 10,000 because it was originally 100. Okay, okay, then go to the job manager here, e-transfer model aborted, so let's submit it again. We like to overwrite the file, yes, and then monitor. Here, okay, the solution started. We don't have got any error. It's going, and you can see the error and also the warning and output at what step the ODB file has been written from these files, message files, and the status files. So these things you can look it from the manual and understand. Okay, so it's continuously writing the ODB file at every second. So let's see, let's wait for the solution. Okay, the solution is completed, and yeah, there is no error message or warning message. Okay, then we can go to the results. Let's go this one, go to the results, and then let's say primary. So this, the temperature field is anti, this is anti 11, the temperature field, and we can animate the temperature distribution in the okay, yes. So from here we can create the XY data and the XY data from the ODB field output, continue, and then it's a nodal. So this is the unique nodal and the nodal temperature, and then for example we can select a node over here in the middle of the beam. Okay, one node selected, then we plot. So this is the temperature versus time curve. Okay, yes, in this way you can simulate the thermal analysis of the section, and this the temperature curve that we have plot over here, this will be the result from thermal analysis, and this we use for the structural analysis. Thank you.